So let me start. Here is the outline of my talk. I will start with motivations from non-commutative Hodge structures and the mirror symmetry. So here we will see all the big picture, the ideas. I think all of you in this homological mirror symmetry conference should know this story very well. And I also, many people explained it many times, but I want to repeat this quickly so that because most of the ideas came from this symplectic geometry and the mirror symmetry considerations. And then I will review what are F bundles and the spectral decomposition theorem. That's also explained in Maxim's talk. And after that, I will talk about the unfolding of F bundles. That's one of the results in my paper with Sogo Ino, Shao Zhang, Chi Zhang, and Changzhen Li, where we also have an application to the mirror symmetry of flag varieties. So all this we did last year. And after that, I will talk about the decomposition of A model F bundles following many results by Hiroshi Iritani, and Maxim also asked me to give a quick overview of Hiroshi's proof. And then we will talk about decomposition, a generalization of these results by Iritani. We will talk about decomposition of quantum cohomology of variations of GIT quotients and flips. This is based on my joint work with my student Zhaoxin Gu and my postdoc Song Yu. And in the end, I will talk about our proof strategy for the variation of GIT decomposition theorem. Okay, let me start. So we have Hodge structure as invariants of complex varieties. Where we have smooth proper complex variety, we get a pure Hodge structure. It's just the decomposition of singular cohomology, and Hn decomposed into HPQ, P plus Q equals N. And we have this complex conjugation of HPQ is equal to HQP. For more general complex varieties, for example, singular or non-proper varieties, we have mixed Hodge structure. And now it has been generalized in this groundbreaking paper by Katsakov, Maxim Kontsevich, and Tony Pontiff. They defined pure non-commutative Hodge structure for smooth proper non-commutative complex variety. And one may ask what happens for more general non-commutative complex varieties. I think that hasn't been studied yet. So just for review, a complex non-commutative space is a C-linear Z2 graded DG category CX, which is homotopic complete and co-complete. So when we have a complex scheme, if we have a complex scheme X, it gives rise to a complex non-commutative space, which is given by the derived category of quasi-coherent sheaves on X. And when we have a DG algebra A over complex numbers, we get also a non-commutative space by taking modules over A. It's called a affine non-commutative space. And this definition, it's also repeated many times in this. I remember many years ago when I came to Miami, everybody talking about this proper and the smoothness as complex non-commutative space is proper if Hom complexes are perfect over C, and it's smooth if it is perfect as a module over this. We have the following conjecture by KKP. So for smooth proper complex analytic space CX, its periodic cyclic homology carries a natural functorial pure Q non-commutative Hodge structure with regular singularities. And furthermore, if this Z2 grading can be lifted to a Z grading, then the non-commutative Hodge structure is an ordinary pure Hodge structure. So if you don't know what is, so this is really generalization of Hodge structure from usual scheme to non-commutative space. And if you don't know what is non-commutative Hodge structure, let me give a quick review. A pure rational pure non-commutative Hodge structure consists of this triple H, E, and iso, where H is a Z2 graded algebraic vector bundle on A1 over U. A1 with coordinate U, and the E, called the Betty data, is a local system of finite dimensional Q vector spaces on A1. -0 and iso is an analytic isomorphism. So between this local system tensor with structure sheaf and with this vector bundle but outside 0. So in other words, we see that this isomorphism gives rise to a flat holomorphic connection nabla on outside 0. It's called the theorem data. And in other words, you can think of this triple as we have a vector bundle over A1. We have a holomorphic connection, flat holomorphic connection outside 0. And then also outside 0, you have a rational structure for the connection. This triple is asked to satisfy three axioms. Non-commutative filtration axiom asks this connection to have a pole of order 2 at 0 and a regular singularity at infinity. So basically, we are asking all the interesting things happens around 0. And we have Q structure axiom E is compatible with Stokes data, meaning that when we try to solve this differential equation for this connection in the sectors, we want all the asymptotics of solutions to be compatible with the Q structure. And also we have a opposeness theorem, generalization of this conjugation identity for Hodge structure. So for example, when we have a pure rational Hodge structure of weight W given by vector space filtration and this Q structure, it gives the non-commutative Hodge structure by the Riesz construction, where we encode. Here we have an extra variable U for a non-commutative Hodge structure, and we use this extra variable U via this Riesz construction to encode the filtration. And then we also have this nabla and the Betty, the Q structure, say. Non-commutative Hodge structure, by definition, it has second order pole. And in practice, we restrict to those of exponential type. It means that when we do this Level-Turretin decomposition after base change to this formal punctured neighborhood, then without further like ramification, it just splits into this form where into the direct sum of this rank 1 bundles with this particular connection given by d minus d ci over u and the tensor with something with regular singularity Ri. When we have, just as in Hodge theory, we not only consider Hodge structure but also consider variation of Hodge structures. Here we can consider variations of non-commutative Hodge structures over some base. So the main example, we have two main examples of non-commutative Hodge structures: A model variation of non-commutative Hodge structures and B model variation of non-commutative Hodge structures from both sides of mirror symmetry. When we have a smooth projective variety, so the A model variation comes from Gromov-Witten invariance. When we have a smooth projective complex variety X over C, and we consider its Gromov-Witten invariance. And here, for the F bond, for the non-commutative Hodge structure, we take trivial bundle with fiber given by the cohomology of X, and we choose a basis Ti, and the base B is given by this formal spectrum associated to the Novikov variables for X and these formal variables Ti for the basis of the cohomology. Then the connection is given by the quantum connection given by these formulas. So in the u direction, we have a second order pole, and u minus 2 term is given by quantum multiplication of Euler with Euler vector field, and first u inverse is given by the grading operator here. Then we also have connection in the tau direction given by quantum multiplication with tau, and the connections in the q directions given by quantum multiplication with these degree 2 cohomology classes. Betty structure, as explained in Tony Pontiff's talk, it's given by image of rational cohomology, but twisted by the gamma class. So conjecturally, this gives an example of non-commutative Hodge structure satisfying these identities, satisfying the axioms in the definition of non-commutative Hodge structure. It's actually largely open, this conjecture, because we don't know convergence, Q structure, axiom, or opposeness, and exponential type is proved by the works of Zihong Chen and Pomerleau, and based on previous works by Pomerleau Saido. So from the B model, we also get a non-commutative Hodge structure. When we have this Landau-Ginzburg model, Y smooth quasi-projective variety over C, W some potential on Y with proper critical locus, we take this bundle to be twisted the Ram cohomology, and the nabula is the Gauss-Manning connection. And the Q structure is given by rapid decay cohomology. So here it's mostly known as opposed to the contrary to the A model case. So here this triple gives a non-commutative Hodge structure of exponential type. Okay. Yeah, so A model, B model, that comes from mirror symmetry. It is a conjectural duality between Calabi-Yau varieties. Initially, we have this formulation. So we have X Calabi-Yau and mirror X check, Calabi-Yau of same dimension, and later it was generalized to over non-Calabi-Yau cases. So in particular, for X Calabi-Yau orthogonal, we can have a Landau-Ginzburg model mirror, where the mirror is not just a variety, but a variety Y plus a function W on Y. The Hodge theoretic mirror symmetry conjecture after the previous slides can be stated very simply, which is just A model non-commutative Hodge structure for X is isomorphic to B model non-commutative Hodge structure for this Landau-Ginzburg model YW. That's Hodge theoretic mirror symmetry conjecture. And we also have this homological mirror symmetry conjecture proposed by Kondasevich, which gave rise to all this sequence of nice conferences in Miami. So here, there are many different versions, and here we are consider B model of X and A model of Y. Probably people are more familiar with. You can consider also A model for X and B model for Y. But here we consider B model for X and A model for the Landau-Ginzburg model, which means we take dB-co of X and the Fukaya-Saito category of YW. Fukaya-Saito category, it's generalization of Fukaya category for this Landau-Ginzburg model case, where the objects are given by these Lefschetz symbols. So you have this potential W, it has some critical values, and you choose these paths, and then we have these Lefschetz symbols over these paths as objects for the Fukaya-Saito category, and morphisms are given by Floer homology. So Here in this for this category, since the objects are just over these paths, and we have a very natural semi-orthogonal decomposition of this category, and that suggests by the equivalence, this picture suggests the semi-orthogonal decomposition of DB-Co, and which further suggests decomposition of Hodge structure for X. And if we think in terms of Hodge theoretic mirror symmetry, then decomposition of B model non-commutative Hodge structure for this YW, it suggests decomposition of A model non-commutative Hodge structure for X. Here I say suggests because mirror symmetry is conjectural in general. And when we get decomposition of A model non-commutative Hodge structure for X, it suggests decomposition of Hodge structure of X via motivic Galois group action, as explained in Maxim's talk for the theory of atoms. Okay. So yeah, that's all about the motivations. Let me move to the actual mathematics. The theory of non-commutative Hodge structures is very powerful. As we see, it's also very involved. But it depends on many hard conjectures that will probably take really long time to get solved. But we really want to extract as many like solid pieces of mathematics and also solid applications as possible from this beautiful theory. So that's why we have all these conjectural objects, but in order to get like well-grounded pieces of math, we try to extract things that we can make sense of without conditional or without the conjectures, without assuming any conjecture. So for this purpose, we ignore complex analytic convergence and the Q structures, and this gives us the notion of F-bundle. In Tony Pontiff's talk, he explained how to get back rational structure or integral structure while still ignoring complex analytic convergence, and that's what we are working on as our subsequent work. Here, we ignore both convergence and the Q structure. So for this purpose, this gives rise to the notion of F-bundle. Here, when we ignore complex analytic convergence, we still want to have a little bit of convergence to make geometric constructions. And here we take base B to be smooth non-Archimedean K analytic space. And instead of considering the whole A1, we consider a germ of A1 at 0. And the definition of F-bundle, it's explained many times in this in Miami. I just give a quick review. It's basically just a variation of non-commutative Hodge structure and forgetting convergence and Q structure by doing it over non-Archimedean space. So an F-bundle H nabla B consists of a vector bundle H over B times the germ and a meromorphic flat connection nabla with poles at U equals 0, such that so we have second order pole in the U direction, first order pole in the other directions, For any point on the base, we get a natural action from the tangent space at little b to the fiber at U equals 0. And the F-bundle is called the maximal at this point B if we have a cyclic vector such that this map gives isomorphism. And in the maximal case, we get Euler vector field because now you consider this residue in the U direction. And since it's isomorphism, we can find a vector field on the base B that gives rise to the residue in the U direction. And also in the maximal case, because this endomorphism has it's commutative here, and it induces a commutative product on the tangent space by the flatness of nabla, and this product is exactly the quantum product in quantum cohomology for the A model. So in general, for F bundle, we have the spectral decomposition theorem. Recall we have this KB, the action of the Euler vector field, and the spectral decomposition theorem says that the generalized eigenspace decomposition of this Euler vector field action extends locally to a product decomposition of the F bundle. So basically, it says that when you pick one point and decompose the fiber there by the eigenvalues of the Euler vector field action, and then locally the F bundle can just be split into a product, both for the base and the fiber. It's just splits into many small F bundles, and this is the main idea we use in the atomic decomposition for varieties. This spectral decomposition theorem, we wrote down the proof in my paper with my students, Ino, Shao, and Chi in this arXiv preprint. So it's phrased in this non-Archimedean setting. B is non-Archimedean. Here we have maximal F bundle, and assume we have a decomposition. It's generalized eigenspace decomposition, or we ask it to be stable under Euler vector field action, and the decomposition have disjoint spectra. Then we can extend this over an open neighborhood U of little b, such that over that neighborhood it splits. Not just the fiber, but everything splits, the base, the fiber, the connection, everything splits. So we proved it by order by order extension plus estimates on the norms of the coefficients to obtain non-Archimedean convergence. And we have to note that here the decomposition works only over non-Archimedean field. It wouldn't work over complex numbers because of the Stokes phenomenon. So yeah, when we consider these atoms and atomic decomposition, we see that the use of non-Archimedean geometry is essential here, since over complex numbers, we don't get decomposition, spectral decomposition. Okay, now I want to talk about another result we did last year. It's for the unfolding of F bundles. So as you have seen, F bundle is really a non-Archimedean or formal analog of this non-commutative Hodge structure or other notions considered by people in the study of mirror symmetry, such as Frobenius manifold, or there is a list of notions considered by Manning and Hartling. And here we also try to see to establish more properties of F bundles for the applications to enumerative geometry and mirror symmetry. So the next thing I want to talk about is unfolding of F bundles. Recall the small quantum cohomology is the restriction of bigger quantum cohomology to all, you just set all Ti to 0, or equivalently set all non-degree Ti to 0. Kontasevich-Manning reconstruction theorem shows that the big quantum cohomology can be recovered from the small quantum cohomology under the condition that the classical cohomology is H2 generated. It's later generalized by Hartley-Manning to the universal unfolding theorem of Frobenius manifolds, where the H2 generation condition is replaced by two conditions called IC and GC. Here we will extend Hartley-Manning's universal unfolding theorem to equivariant F bundles. And for this purpose, we have to consider F bundles over general fields and rings. So recall, this is the definition of F bundle where we have U direction and the B direction. If the connection is defined only in the B direction, we call this a K-linear T structure. For equivariant F bundles coming from equivariant Gromov-Witten invariants, the connection in the U direction is not linear over the base equivariant ring for a point due to non-trivial grading on R. So the associated F bundle can only be defined over the based field K, and hence this F bundle will have infinite rank and depends on infinitely many variables, indexed by a K basis of the equivariant ring of a point, equivariant cohomology of a point. So for this, we need to adapt our previous definitions to the infinite rank case. Yeah, we consider now the base R to be K algebra, and we consider some F bundle over R, but also for some countably many variables. So again, we can consider residue of this F bundle in the real directions, and similar to in the definition of maximal F bundle, we consider this action of the tangent space to the fiber, and for any vector V in the fiber H, we get these maps. So recall the F bundle is called the maximal if there is a cyclic vector making this an isomorphism. And here we further define the following conditions on this vector V. So we generalize the IC-GC conditions in Hartley and Manning's unfolding work to this equivariant and infinite rank case. The IC condition here means that the map mu V is injective, and the GC condition means that the orbit of V under the action of this orbit of V, like generated by the image of mu and K, is the whole H, is H. And we also have a variant GC prime of the GC condition, which is GC after base change to the fractional field. Now we can introduce the notion of equivariant F bundle. So when we have I, a finite set, and a K-linear basis of a K algebra R indexed by a countable set K, we consider this bold Ti to be all these formal parameters indexed by big I and big K, and the little Ti just formal parameters over R indexed by big I. An equivariant F bundle, as I said, you can't really define equivariant F bundle directly because it's just not linear over the equivariant ring. So here, equivariant F bundle consists of first some K-linear F bundle, but with infinite rank, depending on infinite many variables. And furthermore, we consider a R-linear lift to this ring, this base ring of the K-linear T structure. So we see that the trouble of this non-R linearity comes from the U direction. So an equivariant F bundle is really here, it's an F bundle over the equivariant base, but without the U direction, and the U direction is only over the non-equivariant base. So now we can we can state the equivariant unfolding theorem proved in this arXiv preprint with my students Ino, Shao and Chi, together with Changzhen Li. Here, F is the equivariant F bundle. Consider equivariant F bundle, and we show that if this vector V satisfies ICGC with the free co-kernel mu V, then F admits a maximal unfolding with a cyclic vector induced from V. And if V satisfies GC prime, then any two maximal unfoldings of F with cyclic vectors induced from V are isomorphic under unique isomorphism. And furthermore, using the any framing for F induces a unique framing on a maximal unfolding. So our motivation for obtaining this equivariant unfolding theorem is for the application to the mirror symmetry of flag varieties. We apply the equivariant unfolding theorem to the mirror symmetry of flag varieties G over P. So mirror symmetry, small mirror symmetry for flag varieties has been studied for a long time by Peterson, Rich, Lam, Shimozuno, Chong, and Cho on the A side and also on the B side by these mathematicians. And we can combine all this Dubrovin connection and also this Briscoe lattice all together based on all these works to get a small quantum cohomology mirror symmetry in terms of equivariant F bundles. And now we can apply the equivariant unfolding theorem and obtain the mirror symmetry statement for flag varieties in terms of big quantum D module. So as an application of the equivariant unfolding theorem, we show that the A model big equivariant F bundle for flag varieties is isomorphic to the B model big equivariant F bundle for its mirror. Okay, so in the remaining like 25 minutes, let me go back to the decomposition of F bundles, and we talked about decomposition for general F bundles, the spectral decomposition theorem, and the unfolding of F bundles. Let's now focus on this more concrete decomposition of A model F bundles for specific geometric constructions. So here I will review results by Hiroshi Iritani and how they are extended to the form that we use for the theorem of atoms. Let's first look at the projective bundle case. We have X, a smooth complex projective variety, V over X, a rank R vector bundle, and we have projective bundle PV. P, it's a projective bundle, associate projective bundle, I denote by little p, the first chain class of O1. The Leray-Hirsch theorem implies that this cohomology of P, cohomology ring of P, it's cohomology ring of X, it's like a polynomial over cohomology ring of X. You add one variable and the quotient by this by chain classes, by the polynomial with coefficient, polynomial in P with coefficients given by chain classes. In particular, we have a natural splitting of classical cohomology. So the cohomology of P is split into this R many cohomologies of the base X. And the map is given by pullback and take a PI cup product with pullback by pi. And we want to, now this splitting of classical cohomology, we want to extend it from classical to quantum cohomology. Before extending it to the full quantum cohomology, we can first consider this small vertical quantum cohomology. So let this QHSV denote the small vertical quantum cohomology. It's like the simplest, the smallest, a little bit quantum extension you consider by adding only these vertical curves that lie in fibers of the projective bundle. So when we consider small vertical quantum cohomology, it's still very easy to write it. It can be written just as a small variation of the previous Leray-Hirsch formula. You have add this Q is a Novikov variable for this vertical curves, and the small vertical quantum cohomology can still be written as this polynomial algebra. Okay. Yeah. So next, if we want to extend it to bigger quantum cohomology, first we need to really take care of the Novikov rings, because you want to compare a bigger quantum cohomology for or quantum D module for different space. They just have different Novikov rings, so we need to pull back all of them to a unified base. Let's consider Novikov variables QP, QX, and the little q denote the Novikov variables of the projective bundle P, the base X, and the vertical line, respectively. And next, we embed the coefficient rings of the quantum D module of P and the quantum D module of X into this ring. So this ring will be the common base ring. We use these formulas following Iritani. And now we do base changes of the quantum D modules to this common base ring. After base change, it's proved by Iritani and Koto that we have a formal invertible map from cohomology of P to the direct sum of cohomology of X. And then we have an isomorphism between quantum cohomology of P pull back to the unified base ring with direct sum of quantum cohomology of X pull back to the unified base ring, and also pull back by this formal invertible map. This is like a mirror map, and that respects the connection and the pairing. Here, the maps sigma j are defined over, so we have to further invert little q. It was just here. It's more precise. It was the common base ring for the Novikov variables is here, but for this sigma j, it's defined over this base ring, and the isomorphism phi is defined over this ring. So the quantum connection tends to the quantum multiplication. So here we get an identification after pullback of quantum D module. But when you consider quantum connection in the quantum D module and let z goes to 0, we get a quantum multiplication. So when you take a derivative of this map sigma, we get a decomposition of bigger quantum cohomology ring. So the result by Iritani and Koto on this quantum D module also induces decomposition of F bundle for the projective bundle. Here for F bundle, we consider this disjoint union of the base X, R times disjoint union, and now we consider A model F bundle for P and A model H nabla to be A model F bundle for P, and H prime nabla prime B prime to be A model maximal F bundle for X prime with a shifted base point. Yeah, this is one tricky thing in this decomposition of F bundle. that we need to shift the base point for F bundle. We first obtain the existence of uniqueness of gauge equivalence over the base points. And when we try to obtain decomposition of F bundle even at the base points, we will see the necessity of the shift of base point. So here there exists a F bundle isomorphism over the base point between this F bundle for P and F bundle for the disjoint union over the base points B and little b prime, with the condition that the components of this gauge transformation are given by a cup product with elements in the cohomology, if and only if the coordinates of the base point delta A satisfy this formula. So we want the coordinates to satisfy this formula given by first chain class of V and eigenvalues of the Euler vector field action at the limiting point. So you see that if we don't do a base point shift, we wouldn't even get decomposition of F bundle over the base point. And furthermore, in this case, this phi is uniquely determined by the H0 components of phi restrict to u equals 0, and this shift is uniquely determined by this formula up to some shift in H2, which we can't. There's no way to fix. So after the shift point, we get decomposition of F bundle over the base points, and we can extend the decomposition result now over the bigger base. So there is a canonical isomorphism of maximal F bundles between H nabla and H prime nabla prime over an analytic domain U in big B and an analytic domain U prime in B prime. And the union of different choices of U is connected and non-empty, as is the union of different choices of U prime. Furthermore, the bundle map is uniquely and explicitly determined by its restriction to little b, to the base point little b. And the base map is uniquely and explicitly determined by its restriction to the base point little b up to a multiplicative constant in the q direction. So the proof is based on, we need to study the domain of non-Archimedean convergence in the works of Iritani and Koto, and the uniqueness follows from the extension of framing theorem of F bundles. The next geometric construction where we study the decomposition of F bundle is for blowups. So here we have X smooth projective, complex projective variety, and we have this center Z, a closed subvariety of codimension R greater or equal to 2, and we take a blowup of X along Z. We get X tilde to X. We have exceptional divisor D, and here we have the classical result, natural splitting for classical cohomology for the blowup. X tilde, it splits into cohomology of the base plus R-1 copies of cohomology of the center. And we want to extend it to quantum cohomology. So similarly, the first minimal extension we can do is this extension to the small vertical quantum cohomology, and where we consider only vertical curves that are contracted by the blowup map pi. And we get the same decomposition. So the small quantum cohomology of X tilde at Q equals 1 decomposes into, it should be small quantum cohomology, small vertical quantum cohomology of X, and with small vertical quantum cohomology of Z. Sorry, it's just there's no more vertical. It's just cohomology, quantum cohomology, usual cohomology of X and the usual cohomology of Z. So again, to extend this small vertical quantum cohomology to bigger quantum cohomology, we need to embed their Novikov rings to a common ring. And again, here we introduce these Novikov variables Q, Q, Z, Q tilde, and we follow the embeddings given by irritani. And we pull back these quantum D modules to the common base ring via these ring extensions. It's proved by Iritani that we have formal invertible maps from cohomology of x tilde to the cohomology of x plus r minus 1 copies of cohomology of z. And we have an isomorphism, it's like gauge transformation for this quantum D module after pullback to this common base ring and after pullback using this formal invertible map tau and sigma. So this isomorphism respects quantum connection and the pairing. Here it's defined over this ring and the tau and the sigma defined over, it's very precise where it's defined over, and the isomorphism psi is defined over this ring. So again, you can take a limit for z goes to 0, and the derivative of this map induces a decomposition of big quantum cohomology ring or blow up. Maxime asked me to explain the idea of proof of Iritani in this conference. So let me just give you just follow Iritani and explain the idea. So the idea is to realize blowups as variation of GIT quotients. Here we consider W to be the blowup of, consider total space, x times p1, we blow up along z times 0, and we have the rank 1 torus C star acting on the total space W induced by the action on the p1 here. In here, fixed locus contains 3 components, xz and x tilde. There are 2 non-empty smooth GIT quotients of W with respect to this C star action. So it's either x or x tilde. And the equivariant ample cone here, CTW, has 2 open chambers, one for x tilde, corresponding to the 2 GIT quotients, x and x tilde. There are 3 steps of proof. First, Iritani constructed the following maps of D modules as Fourier transforms. So from equivariant quantum D module of W to quantum D module of x tilde by Fourier transform x tilde, and from this to quantum D module of Z by Fourier transform fzi. They're multiples because it's direct sum. It wouldn't be direct sum here. And there's Fourier transform from equivariant quantum D module of W to quantum D module of X. Here, these 2 Fourier transforms are discrete Fourier transforms associated with the GIT quotients X and X tilde defined using shift operators. And this vertical map, they are continuous Fourier transforms for the fixed component Z derived from the given Coates quantum Riemann-Roch theorem. Okay. Next, Iritani considered the submodule given by the action of the shift operators, and we take a completion of this equivariant quantum D module at the x tilde cusp. So finally, he shows that the maps, these 3 maps, Fourier transform maps, extends to the completion and give rise to these isomorphisms. And this is based on the really nice comparison between the discrete Fourier transform and the continuous Fourier transform. So so for the application to atoms, we extend Iritani's result from quantum D module to F bundle. Here we consider X prime to be X disjoint union with these copies of Z, and we fix some ample class. And we consider the maximal A model F bundle for X, H nabla B, base point associated to an F class, pullback of an ample class by pi. And we, again, as in the projective bundle case, we need to do a shift of base point. So for the disjoint union, we need to do a shift by delta A. And exactly as in the projective bundle case, just in order to get decomposition or identification of F bundle at the base points, the shift can be computed. The shift is unique, it's determined, but if we really need a shift of base point in order to get this decomposition even at a point. So here the shift of base points for the shift can also be computed via these eigenvalues. So we computed these eigenvalues. In other words, we consider the roots of this polynomial, and this Ci are the chain classes. And we can compute the roots modulo some hierarchical homology classes. And then we define the shift of base point using these roots. So again, this theorem is similar to the one I explained for the projective bundle case. In order to have this F bundle at isomorphism at the base points, the shift has to be determined by this formula. So it's uniquely determined. And the base point is also uniquely determined. Both the gauge transformation and the base point, they are uniquely determined up to a shift in degree 2 cohomology. After that, we can extend the result over like some neighborhood for the non-Archimedean F bundle. So we can extend over analytic domains, and all the choices, it's canonical extension. As in the projective bundle case, the non-Archimedean convergence is something we need to show in addition to Iritani's formal result. And it's based on this estimates, this lemma for estimating the non-Archimedean, the size of coefficients and the radius of convergence for non-Archimedean over the non-Archimedean base. So here we have this lemma where we consider these maps of these theta algebras, and if we have this bound on the size of the coefficients with respect to degree, then we obtain convergence over this small neighborhood of 0 and this annulus. Y, we get convergence while Y lives in the small disk and P lies in the small annulus. The decomposition of quantum cohomology for blowup, I want to give the geometric picture. It's in fact the eigenspace decomposition of Euler vector field action as we explained in the spectral decomposition theorem at the limiting point corresponding to pullback of an ample class on X. So here we can compute the eigenvalues. They are 0 and this slightly shifted roots of unity. So we have roots of unity here, but you rotate half. And you see this is the eigenvalues at 0 at the limiting, not 0, at the limiting point, and when we move away from the limiting point, every eigenvalue may further split into these clusters. Okay. In the remaining 5 minutes, I'll talk about my work with my student Zhao Xin and postdoc Song Yu. Here we extend Iritani's result from blowups and quantum and projective bundle to the variation of GIT quotients and flips. So yeah, so we know GIT quotient depends on choice of linearization, and different linearizations are parameterized by this EGW, the all ample G linearizations with non-empty semi-stable loci, And this space has a wall and a chamber structure. So basically, you have this wall and the chambers, and in the same chamber, it's the same GIT quotient. And when we go from one chamber to another, across the wall, you get a different GIT quotient. And now we consider two adjacent chambers, and when we will go from one to another adjacent chamber, you get two different GIT quotients, x plus x minus, associated to two linearizations, L plus L minus, and they will be related by a birational transformation f from x minus to x plus. It's called the VGIT wall crossing. So let's restrict it to the case where things are smooth. We call it a simple VGIT wall crossing. And in particular, such a birational map F is a standard flip of this type. And the exceptional loci are projective bundles of different rank, R plus minus 1 or R minus minus 1 over the S, over the wall S. So as a consequence of decomposition of Cho motifs, we have the following decomposition of cohomology for a VGIT, variation of GIT. Here, assuming R plus is less than or equal to R minus, we have cohomology of X minus is isomorphic to cohomology of X plus, plus copies of cohomology of S. And as in the case of projective bundle and blow up, we want to extend the above decomposition from classical cohomology to quantum cohomology and quantum D-module. So similar to the blow up and the quantum and the projective bundle case, we have to unify the base rings. Here in this slide, we discuss how do we unify the base rings in different cases. It's if you just want to get a rough idea of decomposition of quantum cohomology, you can ignore this. But of course, when you really want to write down the exact formulation of the theorem, base rings is a bigger headache. And now I can state the theorem proved by Zhaoxin, Song, and myself. Here, we find a formal change of variables between cohomology of X minus and cohomology of X plus, direct sum with copies of cohomology of S, and after pulling back by this change of variables, we get an isomorphism of quantum D-module between quantum D-module of X minus and quantum D-module of X plus, direct sum with copies of quantum D-module of S. So as in the projective bundle and the blow up case, when we take a limit z equals 0, it gives us a decomposition of quantum cohomology rings for variation of GIT. And when R plus equals R minus, it's actually a reformulation of the Crepant transformation conjecture, and most of work follows from previous works by people, Li, Lin, Q, Wang, on the conjecture. And as you see, this variation of GIT is a special case of this standard flips. And we conjecture in our paper that for standard flips, we have the same decomposition of quantum D-module. And in fact, we prove one case of the conjecture for these local models of standard flips. So in my slides, I also have a few slides on the strategy of proof for this variation of GIT decomposition theorem. The basic idea is to reduce to a 3-component variation of GIT wall crossing. In general, there are many fixed components. We consider the special case of 3-component C star variation of GIT. So and the reduction is made through master space construction of Sadius. Yeah, so I don't have time here, and just want to say that via many reduction steps, we reduce it to 3-component GIT, and we prove the 3-component case. And the main technique used for the 3-component VGIT is again Fourier analysis on this equivariant quantum cohomology. So we consider continuous Fourier transform coming from given Tau-Coates formalism and the discrete Fourier transform given by shift operators. And the comparison between continuous Fourier transform and discrete Fourier transform is based on the reduction conjecture here by Iritani. Iritani proved the reduction conjecture in the special case where in the special case and in our setting, we need to extend Iritani's proof to the more general case of GIT quotients for the highest, lowest GIT quotients. Let me stop here, and that's all I have here. So thank you very much for your attention.